Hi, I'm Christopher Richard, Managing Director and Chief Software Architect at G7CR Technologies India Private Limited, and happy today to take you through the session on behalf of Microsoft on SQL Server indexing. We really hope that you're going to enjoy this video as much as we enjoyed making it for you, and I hope you have a happy learning experience. In this particular session, we are going to cover for you how heaps and table scans work. We'll try and deep dive into I/O and its effect on performance. We'll understand query plans. We'll understand clustered and non-clustered indexes. We'll talk about partition indexes, and we'll understand all those small little operations that happen during an execution plan, like lookup operations, and we'll talk about statistic analysis, and we'll also talk about fragmentation and how you can work with fragmentation. Now that's the agenda we have during this session. Sit back, relax, and hope you enjoyed the session. Now, SQL Server assesses data in two possible ways. Either it needs to scan all the pages that belong to a particular table and find the rows or records that are related to your query and give you the output. Or two, it could use an index to reach only those pages which contain those records that you're looking for and return your results. That's as far as the way it works. Now, if you're looking at indexes and if you're looking at it using an index will always start off with a root page. Right, you can see that right there on top. You have a root page. You will have your key, whichever column you built the index on would be called the index key. You'll have your key, and then you will have a pointer taking you guiding you to the road or the route to reach that particular record. For example, here you can see the root page is taking you to an intermediate page. The intermediate page further takes you to another page where you can actually find the key value. Now, what is there in this last page, that is the leaf level page, totally depends on whether you built a cluster or a non-clustered index. If you're trying to understand what is a heap is when you store data and you don't have a clustered index on that table. Because when you don't have a clustered index, then it means the rows are not sorted in any fashion, and neither are the pages that belong to this table organized in any fashion. Now, because of the lack of organization of these pages, since there's no particular order for the pages or the rows stored on the pages, we refer to these pages as heaps. Now, how to find these pages becomes a pretty simple and straightforward mechanism with Microsoft SQL Server. It will have the address of an IEM page that belongs to that particular table, and on the IEM page it would have the addresses, or rather the pointers, to all the pages that contained data for this particular table. And this is what we refer to as the heap. These data pages that are scattered, or we call them the heap. And you reach the heap by finding the addresses of all these data pages on the IAM page. And you find the IAM page by going to the sysindexes table and looking at a column called first IAM, where you'll have the address of that particular IAM page. Now, in a clustered index, what changes here is now the data is no longer stored in a heap like we discussed on the previous slide. The data now, or the rows, will now be sorted based on your clustering key, that is whichever column you created the cluster index on, and would be stored on the leaf level of the clustered index. You will now need to start your navigation with a root page. The address of the root page again can be obtained from the sysindexes table, and once you get the root page, you will navigate towards the leaf pages which actually have your data record on it. So when you reach the leaf page here, you actually pick up the entire record of data which is stored and sorted. There could be intermediate pages here also, depending on the depth of your index and the number of keys that you actually need to point to and the size of the data rows in that table. All the pages in the clustered index would be organized in the order of the clustering key, and they would all be interrelated like you would see on this diagram right now. You can see what the root page leads you to the next level, or the intermediate pages. You can also see the intermediate pages having a forward as well as a backward pointer so that they could actually navigate between each other. And you'll see the same concept happening to the leaf pages, where all the leaf pages are linked. Now that's a clustered index for you. Now, a non-clustered index has a similar B-tree structure, of course, just like the clustered index, with one significant difference. We have a root page here again, we have intermediate pages that could be possible, and we have the leaf node. The only difference here, like I said, which is significant, is the leaf node does not contain the actual data. It contains a key and a pointer to the actual data. And in this case, or in most cases, the actual data could either be on a clustered index or the actual data could be on a heap. Irrelevant to where the actual data is, the non-clustered leaf node will have a pointer to either the heap or to the clustered index. The root page of this index again would be picked up or fetched from the same sysindexes table like we discussed earlier for the clustered index. Like I said, the only difference here is the leaf page contains only pointers and not the actual data. Another interesting thing is, with the current version of SQL Server, that's from 2012 onwards, you can have up to 999 non-clustered indexes per table, but you can have only one clustered indexes on a table, and this is for all versions of SQL Server, only one possible clustered index. So that's another significant difference for developers and implementers. Ignore the 249 on the slide. In all previous versions, you could have up to 249. From 2012 onwards, we could have up to 999 non-clustered indexes on a SQL Server table. Just for you to be able to understand that better and get a better view of these index structures and heaps, I'm going to show you a small little clipping which would do a good job most probably in helping
Microsoft SQL Server Index Architecture. SQL Server indexes are implemented as a type of balanced tree, or B-tree structure. Similar in concept to a tree, the B-tree diagram consists of a root, non-leaf level, and leaf level. However, in B-tree diagrams, the tree analogy is inverted. Indexes have a single root page. SQL Server always uses this as the starting point for traversing an index. In an index tree, all the index levels above the leaf level, including the root, are known as the non-leaf levels. The leaf level is the bottom level of the index structure. It contains key value index entries that either reference rows in the data pages or complete data rows. SQL Server supports two types of indexes, clustered and non-clustered. Both types of indexes have similar B-tree structures. In a clustered index, the leaf level is the actual data page. For a table with a clustered index, data is physically stored on a data page in ascending order. The order of the values in the index pages is also ascending. SQL Server internally maintains uniqueness of key values for a clustered index, even if the column data is not unique. It does this automatically by generating a value that is stored with the duplicate key value. For example, when the first instance of Jones is entered, all key values are still unique. When subsequent values of Jones are entered, SQL Server generates an internal number that it uses to maintain uniqueness among these duplicate keys. This enables SQL Server to differentiate between all instances of Jones. Let's take a closer look at how SQL Server navigates a clustered index. In this example, a clustered index is built on the last name column. The query is searching for rows where last name is equal to Rudd. SQL Server starts at the root page. It evaluates whether Rudd is greater than or equal to the key value actar. The comparison evaluates to true, and SQL Server moves to the next key value. SQL Server evaluates whether Rudd is greater than or equal to the key value Martin. The comparison evaluates to true and is the last key value on the page. SQL Server moves to the page at the next level to which the key value Martin points. SQL Server evaluates whether Rudd is greater than or equal to the key value Martin. The comparison evaluates to true, and SQL Server moves to the next key value. SQL Server evaluates whether Rudd is greater than or equal to the key value Smith. The comparison evaluates to false. SQL Server uses the previous key value, Martin, and moves to the page at the next level to which the key value, Martin, points. SQL Server reads through the data page until it finds Rudd. It then returns the row to the query processor. Now let's take a look at non-clustered indexes. Non-clustered indexes have the same B-tree structure as clustered indexes, with one significant difference. The leaf level of a non-clustered index contains key values, not the actual data. These key values map to pointers or clustering keys that locate rows in the data pages. The implementation of a non-clustered index depends on whether the data pages of a table are managed as a heap or as a clustered index. In a non-clustered index built on a heap, SQL Server uses pointers in the leaf-level index pages that point to rows in the data pages. If you have a table with a clustered index, SQL Server builds the non-clustered indexes on top of the clustered index structure. In a non-clustered index built on a clustered index, SQL Server uses clustering keys in the leaf-level pages of the non-clustered index to point to the clustered index. Now let's take a closer look at how SQL Server navigates a non-clustered index on a heap. In this example, a non-clustered index has been created on the last name column. The query is searching for rows where last name is equal to RUD. SQL Server starts at the root level of the non-clustered index. It evaluates whether RUD is greater than or equal to the key value actar. The comparison is true, and SQL Server moves to the next key value. SQL Server evaluates whether RUD is greater than or equal to the key value Martin. The comparison is true. Martin is the last key value on the page and evaluates to true. As a result, SQL Server moves to the next level to which the key value Martin points. SQL Server evaluates whether RUD is greater than or equal to the key value Martin. The comparison is true, and SQL Server moves to the next key value. SQL Server evaluates whether RUD is greater than or equal to the key value Smith. The comparison is false. SQL Server uses the previous key value Martin and moves to the page at the next level to which the key value Martin points. SQL Server reads through the leaf page to find RUD, and then uses the pointer to locate the data page in which the key value is equal to RUD. SQL Server returns this row to the query processor. Now let's take a look at how SQL Server navigates a non-clustered index using a clustering key. In this example, a non-clustered index has been created on the member number column. The table has a clustered index defined on the last name column. The query is searching for member numbers that are equal to 6078. SQL Server starts at the root level of the non-clustered index. It evaluates whether 6078 is greater than or equal to the key value 1234. The comparison is true, and SQL Server moves to the next key value. SQL Server evaluates whether 6078 is greater than or equal to the key value 5678. The comparison is true. 5678 is the last key value on the page and evaluates to true. As a result, SQL Server moves to the next level to which the key value 5678 points. SQL Server evaluates whether 6078 is greater than or equal to the key value 5678. The comparison is true, and SQL Server moves to the next key value. SQL Server evaluates whether 6078 is greater than or equal to the key value 7678. The comparison is false. SQL Server uses the previous key value 5678 and moves to the page at the next level to which the key value 5678 points. SQL Server reads through the leaf-level pages until it finds the key value 6078. This key value maps to the clustering key value RUD. SQL Server uses this value to navigate through the clustered index from the root level to retrieve the row in which RUD is the last name. In summary, the leaf level of a clustered index is the actual data page. Data is physically stored on a data page in ascending order. The leaf level of a non-clustered index contains key values, not the actual data. These key values map to pointers or clustering keys that locate rows in the data pages.
Excellent. I hope that gave you great clarity on index structures and the architecture of how indexes are stored and data is retrieved from them. Before we go on to our next topic, we have a small quiz for you. Just remember, you need to be viewing this video in browser, the HTML version of it, if you want the quiz to work. So enjoy the quiz. I'll see you back with our next topic once that is done. Excellent. So you've now seen how indexes work and how their architecture is and how they are actually organized. Let's move on to understand what happens when you run operations on tables that have indexes. The first challenge that you have is now when the data is stored in the heap, the good thing about it is there's no sort order of the records. So you could have data going onto any page as long as the space is available when you work with heaps. But because of the nature of indexes, where indexes are organized and sorted, the minute indexes are built on a table, let it be cluster or non-cluster, any insert, update or delete will now need to ensure that the index also gets updated, and this update would not be a random update where the data could go anywhere. The data will have to be maintained in order. The example on the slide that you're looking at is we are trying to insert the last name Jackson, and we already have an index built on the last name Jackson. So if you're looking at the leaf level pages here, you could see the last names are sorted in alphabetical order, A, B, C. You can most probably see that right now, G, H, J, L, M, and so on. So everything is sorted. Now the new insert that you're trying to make is Jackson, and Jackson will have to come onto the second page on my slide here. Now, if this page has space, wonderful. It simply goes and inserts it. So that's it, finds the page where Jackson has to go using the index and goes ahead and inserts that row there. But if the page has no space, we have an operation. We will have a problem because we cannot put it anywhere. We'll have to still put it in order. So what happens is what we call a page split. If you're going to look at this animation right now, we first go and we find the page where Jackson is supposed to be inserted. And you see what happened just now? That page got split in two. The page got split in two. And now you can see we've got G, H, J, and you can see the order is still being maintained right now. Although now these two new pages do have at least 50%, approximately a 50% freeness on those pages. Now, as you insert more records, of course, that fullness could get used, or if you don't insert any more in between G and J, most probably you may not have anything else getting inserted on these pages. The overhead here that you need to remember is that this will cause an overhead. You don't want this happening too often, page splits, because finding a free page, allocating that page, moving half the data from one page to another page, this is a lot of work, and this will slow down your insert operation. So one, you need to avoid page splits. You need to try and see that this happens lesser frequently. Now, in order to do that, one thing which you could do is when you build your indexes, the original fill factor of the pages, leaf level pages, is around 99%, which means you have enough space. It's not really 99%. It's something like this. You have enough space for one new record. That's the default fullness of your leaf pages when you create a new index. Now you can override that by setting a fill factor value. You can say, for example, you can look at it on the slide when building the index or rebuilding the index, you can set a fill factor of, let's say, 65%, which means the page will be 65% full and 35% would be free. The good thing about this number is it will allow you to now ensure that splits will not happen for at least some point of time, some period of time, because there is free space in the pages. Splits will not occur. The bad thing is this would increase your I/O because you've actually increased the total number of pages that you need to retrieve when you need to take data from this table. Because since the pages are only 65% full now, very naturally you've increased the total number of pages. Now, the higher the total number of pages, the more pages you need to most probably touch, and thereby you've also affected the I/O. So you'll need to consider this carefully as to what fill factor is ideal for your environments. Using a low fill factor for OLTP applications is highly recommended because you'll have a lot of inserts coming in, and using a high fill factor for OLAP is what is recommended because most probably those inserts are going to be once a day. Now, fill factor will help you only set the fullness of the leaf level pages. If you want to do this for the non-leaf pages, you will need to use another option which is called pad underscore index. You can see the syntax of that on that slide there in case you wanted to use it. So that's some of the maintenance activity which you'll need to do. Apart from rebuilding indexes and setting fill factors, there's another thing about indexes that you might need to understand and work with, and that is the fragmentation. Because when splits occur, a new page gets created, a new page needs to be allocated. Now this page may not really be available just next to the existing page. So this page could be available wherever there is a free page. And in time, the more splits occur, you will see your index is completely fragmented. You would like to bring all your index pages together. In other words, you'd like to defragment them. So that would be another thing which you'll need to most probably observe and try and work with. Now there are plenty of ways to monitor and get obtain index information. We have a series of DMVs that we can use for it. We can use the management studio. We can use sp underscore help stored procedure. Or we can use sp underscore help index stored procedure. So quite a few methods are available for us to basically pick index information. I'm going to open up my VM right now and take you through a demo to show you some inputs about indexes that we have. We'll do that right away, where I'll first connect to my remote desktop, and I will connect now to my virtual machine, and let's do some demos on understanding the indexes that we've learned so far. So I open the SQL Server Management Studio here. I connect to the instance that I have, and what I'll do is I'm going to create a new database for the sake of this. I'll call this database the test database, and I'm going to run a query in the test database which is going to pick up some data for me. To start with, I'll say select star from, or rather I'll say select star into, let's call this table X, from northwind.dbo.customer. So I'm picking up data from the Northwind customers table, and I'm putting it into a new table called X91 records get inserted right there. Now the first thing I would like you to check would be the select star from sys.sysindexes, where id is equal to object underscore id, and we given our table name here X. So this is a good place to actually start off. Now what I'd like to point out here is the ind ID, which is here, which says 0. Now whenever you see this ind ID as 0, you need to understand that this table is currently located on a heap. That means there is no clustered index currently for this table. You can see 91 rows here, 4 used pages, 3 data pages. That's one of the IAM page. You've already seen this before, so you most probably understand that. What I'll do next is I'm going to type in sp underscore help index, and I'll put in there my table name X. I'll execute this, and it says the object X does not have any indexes, or you do not have permission. So right now this table has absolutely no indexes. I'm going to now say create non-clustered index. Let's name this ncl underscore just executing a query there. Let's build this index on the contact name. So I'll call this ncl underscore contact name on. So create clustered index, name of the index on the table called X, and the column called contact name, contact name. So I'm building my first clustered index on this table. I go back to, my first non-clustered index. I go back to my sysindexes. You will see one new row appearing now for this index here. You'll see an ind ID 2 appearing. Ind ID 0, this was the old record which was there. D pages were equal to 3. Now the used pages have gone up to 6. The reason being is there are 2 pages being used by the index that you just created, the non-clustered index. So 3 data pages, 2 pages used by your index, that's 5 pages, and 1 page used by your IAM, that equals to 6 pages. Now the index which you just created is a non-clustered index. You know that because when you have an ind ID which is equal to or greater than 2, you know this record is for a non-clustered index. And the important feature here is you see address here called root. I'm going to copy this address. I'm going to say I'm going to paste that here. Now this is the address of the root page of the non-clustered index which I just built. I'm going to do what I showed you in the other video. I'm going to split this now into two values. The 0x gets removed because the 0x only means that this is an hexadecimal value. Now I'll put in 0001. I'm reversing it now. So I've taken the address of the page. This is so what have I done? I took the address of this page, I removed the 0x factor, I split it into two digits each, and then I reversed the numbers. I've got 0001. I just brought what is towards the end here to the beginning. I reversed it, in other words, and now I will split this up this way. Now these 4 digits represent the file number, so that is file number 1, and I'm going to just open my calculator here, and 133 here represents my page number. So I'm going to go to my programmer calculator here, and I'm going to actually say I've got her hexadecimal value, which is 133. That's my hexadecimal value. I'm going to convert it to decimal, and that tells me 307. So technically what I have here is page number 307, file number 1, which happens to be the root page of this non-clustered index which I built on sysindexes. So that's the interesting factor here which you could actually work with. What I'll do now is I'm going to show you a command which will help you print this page so that you can actually view it. So we had this page number 307 here. So what we're going to do technically now is we're going to print that. For that I'm going to say db cc trace on. I'm going to enable client-side tracing. 3604 I believe is that flag number, and I will execute a dbcc trace off 3604 again. I will now type a dbcc print command here. Sorry, dbcc page. Now the dbcc page command needs information from you such as the database name, which in our case is test. In this database, which file, that is file number 1, and which page are we looking to print, which is page number 307. And here we have a flag which will specify where you want only the header or you want the whole page. Now 0 would mean you'll only get the header printed, 1 would mean the entire page will get printed. So I'm going to execute that, and I've got this root page of this non-clustered index printed right now. The interesting thing is, since we've got only 2 pages in this index, I'm just going to go to the bottom of this page here and show you the offset. Now if you look at the row offset here, you will see this row offset actually contains 91 pointers in it. So actually this index is only a single page. The entire 91 rows, because this is a small table, this happens, the entire 91 rows currently is available in the root page itself. So you can see here the offset. And since we built this on contact name, you will be able to see Alejandra Camino. You can see this name right here. Okay, this is your non-clustered index key value. This is the contact name. The rest of it is the pointer, which is basically telling you where you need to go to get the entire record on the heap for this particular record. I'm not trying to interpret this for you today in this session, but that's what it is. You can see the second contact name here, the third contact name, the fourth contact name. So all you have in the non-clustered index root here is the key value and a pointer telling you where that record actually is located or exists. Going back to the sysindexes, we could do something else here. We can also try and pick up where each record, which is the data pages on the heap, which actually store this record. For that, I'm going to use one of my commands. Now, this command, I would like to caution you, please don't use this anywhere in your production systems. This is an undocumented command. So caution, please don't use. Okay, use it only maybe in your test machines or your other machines where you'd like to basically work with. Don't work with this command in your production machines. Now this is an undocumented function. You can see me highlighting it right here. So what I could actually do right now is I could say give me the address of the table and I can basically pick up the rest of it right here. So I'm going to execute this right now. Sorry, I don't have a column called ID either. Let me just remove that. So I'm using an undocumented function here, and you could see here now I get the entire address of this page. Now I can interpret this in the same way. The only difference is this address will have not only the row ID and the page, it will not only have the file number and the page number, this address will also have the row number to it. So using this, I'm picking up each record on which page it's located. I'm picking up the address of each record. This doesn't look very understanding to you right now. So what I'm going to do is I'm going to use another undocumented function here, okay, which is the function physical log formatter, and I'm going to put in this address which I got from here, right here. I'm just going to highlight this command so that you can see it completely. Okay, so I'm using two undocumented commands here, one to get the physical location and one to format that location so that we'll be able to understand it and interpret it better. Now if you look at this here, you can see I've got it on file number 1, page number 304, row ID 0. That's where the first record is located. You can see all of these rows are located on page number 304. Then you see 305, and then you see 306. Now if you remember this particular table, we seen 3 data pages, and those 3 data pages are 304, 305 and 306. So this is data stored on a heap. I'm showing you the demonstration of understanding where it is. You can get information about it, you can understand which page it's located on, and so on and so forth. You can also pick up information about your index, and you just seen me print a few minutes ago. We printed the address of the root page of the non-clustered index that we were working with. Now I've shown you another command where you can actually pick up your data pages. Even if it's on a heap, you can go out there and pick up each record and find out where exactly each record is. The next thing which I'm going to do is I'm going to drop that non-clustered index. So I'm going to say drop. Now what did I name that index? NCL underscore contact name. So I'm going to pick up that index here. I'm going to paste this here and I'm going to execute it. So I've dropped the non-clustered index now. So I got a table now which is back to having only ind ID 0. You can see I'm back. I've dropped that index, and I'm going to convert this now from a non-clustered index to a clustered index, and I'm going to build this on the column called customer ID. So I execute this command now. So I've created a clustered index this time around. When I go to my sys indexes, unlike last time where I seen 2 rows when I built the non-clustered index, I will end up seeing only 1 here now, because what happens is ind ID 0 goes away and in place of it you get ind ID 1. The reason, because we don't have a heap anymore. Now the data is stored on the on the leaf level of the clustered index. I'm going to pick up this root address of this clustered index once again, and let's go back to interpreting it the way we do. I'm going to paste that here, and this is going to be most probably 3, 6. Split it into 2. This is the reverse bit algorithm which is used for these addresses. So that's the reason I need to do this, to be able to get the right address. 0, 0, 0, 0, 0, 1, and we've got a 36. So this would be file number 1, and page number is 136, but that's an hexadecimal value. So I'll go to hex, I'll type 136, click on decimal, and I've got that page number as 310. I'm going to go into this now. Understand this here. We've got 3 data pages. Now the data pages are no longer unorganized pages on the heap. The 3 data pages here are the pages which are pages which belong to the leaf level of the clustered index. I've got used pages as 5, where one is a root page and one we still have an IAM page, of course. So you have an IAM page, but it won't be used anymore. Now on, whenever the system wants to read data, you will go to the clustered index root page and pick it up from there. So that's my pages accounted for. Now I'm going to print the root page, which we just now decoded, and we decoded it as page number 310. So I'm going to print page number 310. Let me execute that. And here you will see the number of pointers on this page are only 3, so you can see the root page currently points to 3 pages only. So there are only 3 rows here, 3 offsets here, and the offsets would be alphabetically sorted. So let's look at this ALFKI. So this is the beginning, this is 1 pointer, and then we have the name starting with Greel, which is the 2nd pointer, and the name started with Qeed, which is the 3rd pointer. So there are 3 pointers here. I think you can almost visualize this right now. You've got a root page with 3 pointers to it, and these 3 pointers are pointing to 3 leaf level pages. And since this is a clustered index, the leaf level page now will contain the actual data row. I'm going back to my undocumented command here. And let's pick up the way the data is sorted now. You can see we've got page number 307. 309 and 311. So that's the 3 pages currently being used: 307, 311 and 309, the 3 pages which are being used by this. If you try and pick up the number of records in 307, let's have a look at this. You can see the row ID starts from 0, so it goes on to 5, 6, 7, 8. So you've got 16, 20, 30. Now this stops at 30, which means there are 31 rows on page number 307. 31 rows are stored on the leaf level page 307. Let's go and check that out. So I'm going to change this now to 307. And I'm going to print that page for you. So we ran the trace command, so 307. Now what we did notice is 307 stored 31 rows. So I'm going to now go ahead and look at this, and you can see the offset here, which starts from 0, goes to 30. So that's the 31 records stored on 307. Also, if I go to the top here, I will notice the first row is for customer ID ALFKI. And if you go down to the last row, this will be just before the word Greel, because from Greel onwards it is stored on another leaf page in the system. So I'm just going down here further. You can see we've got till F, and we've got to G here, but that's GO URL Gaul, and GREAL goes on to another page. As in simpler words, these are things which you can use to monitor where your indexes are, how data is split across them, how they are stored. You can also use the Management Studio itself to pick up information about your indexes. For example, I'll go to the DBOX here, I'll drill down indexes here. Here is my index. I can right click here on this index and say properties. Now in the properties here, I can go to the storage properties, and in the storage properties, I can go to the fragmentation, and you can see here the total fragmentation currently is 66.6. Excuse me, so sorry for that, excuse me. Okay. The total fragmentation here is 66.67. Okay. The average row size is 259 bytes. We can see the depth of this index is 2. So great, guys, you can actually see the depth of your index right here. The leaf level, total rows stored on the leaf level is 91. The maximum row size is 344. The minimum row size is 186. The total pages is equal to 3, which is being used. And this particular index has only one partition with it, so you can see only one partition. So this gives you quite a bit of information about your index in terms of, you can also see which file group it's stored on. And these are the options which currently your indexes use. You can see the allow page locks. You can change these options at any time you want, but these are all the index options which are available currently. So I'll just say cancel that. So you can also get information about your indexes using the GUI using Management Studio. Like you just seen, you can go to the properties right there and you can get information. I got another query which I use pretty often. I love that query because I use it pretty often when when I go to a system where I don't know how many indexes are there in that database and I just want to find it out. I can actually use this query. It's a pretty longish query for you to type, but it simply goes in and picks up data. I'll try and interpret that for you as much as I can. It goes and tries to pick up data from various system tables and tries to give you the results. I'm going to do this now with the Northwind database. So I'll go to the Northwind database. I'll paste that query there and I create a CTE here. And this CTE is picking up data from the sys.indexes table, the sys.indexes columns table. It also tries to pick up data from the sys.columns and the sys.tables. So these are the tables being used in my system: sys.indexes, sys.index columns. We've got the sys.columns and sys.tables. And these are the values we are picking it up. Now this one, the good thing about this query is, okay, I'm just freezing this on the screen for a couple of minutes here. So for those of you who want, and what I will do here is I will also try and push this a little back so that you can pause this video and actually copy that syntax if you wanted to. That's what I'm trying to actually do right now. Let me just get this fully for you on the screen. Excellent. That query is completely on the screen there. So for those of you who'd like to take down that query, you most probably need to take the trouble of typing it only once like I do. I've got this stored with me always wherever I go, so I just have to copy paste it again on any environment I work in and execute it. Now what will this query do for me? Now when I click on the execute button here, he goes into the Northwind database, he picks up every single table which are there, he tells me the type of index which I have and whether that is a primary key or no, and on which column that index is being built, including telling me about composite indexes. You can see this is a composite index. So this is a great query for those of you who are going to work on a system that you really don't know anything about. You can just run this query because it will pull up a single report, a single table, giving you all the current indexes which are there on all the tables, including telling you the names of those indexes, the type of the index it is, the columns which are being indexed, whether it's unique or not unique, or whether it's the index is on a primary key or no. So this is great information to have. So you got this from this video. Hopefully you've been able to, most probably you can pause that video and take down that entire query in case you wanted to. Okay. So that's one of the queries I use to get index information for me. You can there's lots of other ways, plenty of other ways of getting index information. You can find out the fragmentation of an index and so on using another query that is a physical stats. This is a DM. So I'm showing you another query to pick up information about indexes. Okay, here you go. So I'm going to put in now the DB ID here as Northwind, and let me put in the table here as DBO dot. You can have this flag here as either detailed or I just execute that query, or limited. Limited will give you lesser information, detailed will give you a complete detailed report, and here you can see I've got complete information about the indexes which are available on the customers table in the Northwind database. So I've got a clustered index here. Okay, you can see the depth of the index, you can see the index level, you can see the percentage of fragmentation. Currently there's no fragmentation on this particular index because it's a new one. You can also see the page count, you can see the record count, you can also see the minimum record size, maximum record size, you can see the compressed page information. So all of this is available for you using the DM_DB index physical stats. So this is another way you could use to monitor information and get information about your indexes. So what we've discussed so far is you've learned how to create indexes, you've learned how to manage indexes. Let's switch back to our PowerPoint and talk about some more things related to the management of indexes. Now the index fragmentation, as you've understood, now as page splits occurs, indexes could get fragmented, and when they do, you'll need to actually rebuild those indexes, or you'll need to defragment those indexes. In a minute from now, I'll tell you when you need to do what. To detect the fragmentation, you can either use the properties of the index in the management studio, like I shown you to do, or you can use the DMDB index physical stats, which I also shown you that query for. Now you can reorganize your index if the fragmentation is less than 30%. The command to reorganize your index, you're looking at that on that slide deck right now, so you can use that command, so you can reorganize it. Now what a reorganize does is, it defragments your index. That's it. It doesn't do anything more. It tries to bring all the scattered pages of your indexes together and tries to put them together in one location, thereby defragmenting it. Now this is recommended if you have less than 30% fragmentation. Now what a rebuild does is, it actually drops your index and rebuilds it completely. So in this particular case, what happens is your total index gets rebuilt with the fill factor getting reset, statistics getting rebuilt. So it's as good as you basically executing the create command. However, the alter command is better because it picks up it uses the existing index first to pick up the required information, and once it's got that information, it then drops the existing index and builds a new one. So that's what the alter does. So alter in quite a few cases could actually be faster than a reorganize. I've seen that happen quite often, because reorganizing is a lot of work in terms of you reorganizing things, while as rebuilding is simply drop and recreate again from scratch. And pretty often rebuilding could be faster than reorganize. So general recommendation here, but you can change this based on the systems you work on. If the fragmentation percentage is less than 30%, try reorganizing your indexes. If the fragmentation percentage is greater than 30%, try rebuilding your indexes. Now that's about fragmentation and how you can actually maintain fragmentation. Another great way of working with systems that you really don't know anything about, you don't have a clue about. Now if you're one of those consultants, you go to a system and you're asked to basically build an indexing strategy on that system. It could be a great challenge for you, because to be honest, how do you answer the question as to which is a good index and which is a bad index? You really cannot answer that question. In fact, whenever I hear people saying, I recommend a clustered index for this, I recommend a non-clustered index for this, I really try to figure out what they're talking about. As we go into query optimization in our later videos, where we'll try to basically ensure that queries run quickly, you will learn the importance of I/O. Now when we talk about I/O, now whether an index is good or no, totally and completely depends on the amount of pages you will touch using a particular index for a particular query. So when I make this query, let's say we've got a sample query with us. Now if there was a non-clustered index on a particular column and I ran this query, what we need to check, or what we need to calculate, is what will be the total pages touched by this query using this index against the other indexes. Make these calculations. Now for those of you who don't know how to make these calculations, I promise you we'll do this in our video on optimizing code. I will show you how to do that. So you count the I/O. Whichever index gives you the lower number of pages, that is the better index. Now having said that, okay, and you are understanding the criticalness of I/O. And in today's world, we work in a drastically changing world. Our modern systems, modern hardware has been changing, has grown leaps and bounds from what it's in terms of capabilities, or what it was earlier. But one thing we have noticed is our storage technologies have not been able to keep pace with our processing technologies. For our storage technologies to become more faster in today's world, there needs to be something really drastic that needs to be invented. We need an innovation. We need a breakthrough. The general performance improvements of storage has already been done. For anything greater than what we see today, we need a real breakthrough. And in spite of this, today the biggest problem related to performance in a relational database would be related to I/O. The reason being is reading and writing is slow. I've monitored a lot of systems plenty of times, and guys, I've never, very rarely seen problems related to processor utilization. Most of the time the problems are about the amount of time it takes to read and write from the hard disk. The importance of I/O, the significance of I/O is very clearly understood here. Is if you reduce the amount of pages that you're touching, you actually reduce the amount of reading. Now, you reduce the amount of reading, you automatically have improved your system performance because you didn't have to read. That's one thing. That's only one thing. The second thing is every page is not read from the hard disk. It's read from the hard disk, brought into the buffer, and then read from the buffer. So guys, the lesser pages you bring to the buffer, the more space you have in your buffer, the more lesser memory you actually land up using. So if you're ever working on query optimization, guys, one of the critical things that you need to really optimize is the I/O. You need to ensure that the pages, the lowest amount of pages, are used for the queries that are assessing it. Now this is a challenge, because a particular index could be very good, the I/O could be very low for one query, while as the same index for another query could be causing a very high I/O. And you'll have to make a choice. So in fact, this is most probably, I would say, the most challenging thing. Because if you give me a single query and tell me, Chris, can you optimize this for me? I would. I would optimize it to a level where it would run wonderfully. But guys, while optimizing this query, I may not have considered the impact I'm having on all the other queries that are running on that system. So for you to be able to really come up with an indexing strategy to optimize your overall system, not only should you be familiar with the data sources and the structures of your current tables, you need to also be totally comfortable about the business usage on that database. You need to know which are the queries which are high priority, which are the queries which are not high priority. You need to know which are the where conditions that are used most often, which columns are used in where conditions. You need to most probably be familiar with which are the tables that are most often joined, which of these queries which are using these joins are high critical queries, and which of them are not that critical. Now guys, in simple words, you need to really understand the whole system to come up with an indexing strategy. Sometimes this might be feasible in the real world. Maybe you've been working with this system for maybe the past 3 years and you're very familiar with the system in terms of its usage, in terms of its structures and so on. Great. You would be able to come up with an indexing strategy just sitting down across a table with a pen and paper in your hand. However, that may not be the true scenario most of the times, and in most of the cases you are given a system where you don't know the table structures as familiarly, as clearly as you require to know them. You don't understand a word about usage, and still you are called upon to optimize or improve the performance of that system. In these scenarios, you can use what you're looking at on the slide, the Database Engine Tuning Advisor. Now what you really could do here is you can create a workload, you can start a trace of a regular workload and let that trace track the activity for one full day. Then you feed in to that in the database tuning engine tuning advisor, you feed in that workload and you ask him, can you please now look at this workload and make recommendations for me as to which columns need to be indexed and which existing indexes need to be dropped. He does a pretty good job. The only bad thing about this particular aspect would be is he may not know how to prioritize and deprioritize queries. So apart from that, he does a pretty good job at giving you good recommendations, which you can at least start off with and later continue to fine tune. So my advice is please use the Database Engine Tuning Advisor in such scenarios. It's a pretty useful option that you could actually work with. Now that's about indexes and how you could actually work with indexes and so on. I don't have a trace file with me, so I'm not going to use the Database Engine Tuning Advisor, but that's a wizard, it's a UI, so if you simply go to your system and start to open up that wizard, most of the options are pretty self-explanatory. Just start a SQL profiler trace, create a workload file, and then feed in that workload to this engine tuning advisor, and you do very little there apart from click on next. You will give you the recommendations, and the best thing about it is you can also just click a button and have those recommendations applied. So that's the greatness about the Database Engine Tuning Advisor. My recommendation is to use it. Now you'll have a quiz now at this stage to see whether you got a hang of things that we've communicated so far, and then we'll come back for the last topic in which we'll discuss statistics and execution plans. So we'll be doing statistics and execution plans after the quiz. See you then. Well, let's cover the last of our two topics, index statistics and execution plans. Now, let's start by understanding what exactly is statistics and why it is required. Now, statistics is information given to the optimizer in order to help the optimizer build the right execution plan. Let's think of this from a scenario where, let's say you need to travel from your home to office, and let's say you're doing this for the first time, and you need to plan which would most probably be the best route, the fastest route rather, for you to actually take. Now, guys, in order to do this, before you really even make a choice of this route, you might need to have some information about these routes before you could make that call. For example, you might need to have some information about whether any construction work is going on some of those roads, whether there are any blockages on some of those roads, what is the kind of traffic levels on that roads during peak hours or non-peak hours. In other words, you'll need to have some information to make that decision. Now, the optimizer is very similar. It needs to make a call on which is a better index, for example. It needs to choose which index to use. Now, how will he make this call if he does not know what is going to be the IO for the query? Now, in the earlier session, I remember telling you that the index drives the IO. Using an index, not using an index will decide what is going to be the IO. The optimizer wants to choose the index which has the lowest IO. In order to do this, he needs some information as to what is going to be the selectivity of your query. So he needs to make a prediction on what is going to be the amount of rows returned by your where condition without even executing that query. Now, to do this, he uses statistical information. By default, SQL Server automatically creates statistics on all columns which are used in a where condition, or all columns that are used in a join condition. I'm going to take you through a demonstration now to show you how statistics is used, how they get created, and we'll also during the process understand execution plans. So I'm just switching over now to my virtual machine. Excellent. I'll just close up these windows right now. And let me start by explaining to you the auto create stats that we actually have. I'm going to put in a new query here. Let me do a cleanup. I'll drop table X, which was the table which I created long back, and I'm going to recreate that table as a fresh one. Create table, or rather I would say select star into X from northwind.dbo.customer. So again, creating a fresh new table called X, which has 91 records in it. Now, the important query here for me at this stage would be a query on the sys.sys indexes to show you some information about this, where ID is equal to object underscore ID. Sorry. And now I'll put in my table name there called X. I'll just pick up the columns that are relevant for us right now. So I'll pick up the ID, the ind ID, the D pages, the used pages, the addresses such as first IAM, root, rows, name, and I'll pick up one column that you cannot really read, but I'll pick up that column. It's called the stat blob column. I'm going to execute this right now, and what you will see right now is that the same heap data stored on a heap, no indexes currently on this. So I'm going to say sp underscore help stats, help index X. Execute that for you, and you will see there are no indexes on the table X. Again, I will execute sp underscore help stats, and I'll put in the table X, and I'll execute that for you, and it tells you the object has no statistics. Now I'll execute query on X table, and I get 91 records, which throws up. I recheck my sysindexes, and you'll still see only one row here. I recheck my help stats, and you'll see no statistics still available for this table. At this stage, I'd like to point out to you a property at the database level which can be set. If I go to the options in the database, you will notice I got an auto create statistics set to true. This is the default option. I also got an auto update statistics set to true. So when I try now to create, I'll try now to change this here, where I'll put in select star from X, where customer ID is equal to ALF KI. So I'm just putting in a where condition on the customer ID column. I execute this right now. I go back to my sysindexes and check this here, and you will be surprised that there's one more record now created, although I did not create an index. Now this was the statistics that got created by the system. Now the system created statistics for this where condition because the system had to predict the selectivity. One row threw up for this where condition, but the system had to make a prediction of that even before it executed that query. Let me go to the query bar here and say include the actual execution plan. I'll go to the execution plan of this query. You'll see we did a table scan, but if you put your mouse over that table scan, you will see something here called estimated number of rows. If you can look at that, I won't be able to point out that to you. If you can look carefully from the bottom, this would be the sixth row. If you're counting from the bottom rows, estimated number of rows is equal to 1. The actual number of rows is equal to 1. Now this estimation of number of rows took place even before executing the query. It took place without executing the query, and this estimation was made because statistics were available. So he needed the stats in order to make that estimation. So since stats were not available on the column called customer ID, the system went ahead and built stats. You see when I run the sp underscore help stats now, you get the statistics name here, and you get the column on which the system actually built that statistics. So the system automatically builds statistics for you on columns that do not have indexes. Now see, if you have an index on the column, the good news is statistics are built for that column along with the index. So if you have a column that is not indexed and is used in a where condition or used in a join condition, the system will automatically create statistics for it like you just seen happen. I'm going to do a cleanup there. I'm going to say drop statistics. X comma dot problem. I need the name of the statistics, so I'm going to copy that and paste it there. And now I'm going to execute that. And there the statistics actually got dropped. So it was as simple and as straightforward as that. Now statistics gets created. Now statistics is what? What does he actually create when we are talking about stats creation? Let me just open a new query window to put down those points for you. 1, he picks up a set of samples. The max number which he will pick up would be 300. These samples are called steps. So when we said build statistics on the column called customer ID, the system went into that entire data. So it does a scan of the data. You can decide whether it does a sampling of data and from there picks up the sample, or it does a full scan. The default is a full scan. So it does a full scan of all the values inside this customer ID column, picks up a set of samples which it thinks are required in order to make a prediction as to how many rows will be returned when you work with this column, when you make a where condition on this column. Second, it analyzes and stores density information. Now density information is a number which will identify the number of duplicates, or rather the uniqueness of the values in that column. So you have a set of samples, you have density information. Now when you make a where condition on this column, the system runs that where condition on these samples and gets the result. Then it applies an algorithm, statistical algorithm, on this result along with the density information that it has with it, and makes a prediction as to how many rows this query is going to throw up, or this where condition is going to throw up. Now since he knows the number of rows, he will then use this information to find out what will be the IO in order to throw up these rows if the indexes that were available were used. and then he chooses the index that gives you the lowest IO. Okay. So this is statistics. Now see, interestingly, statistics got built right now. The problem with it is, as you keep inserting, updating, and deleting data, values keep changing. Now when the values change, your statistics would become old, because you collected statistics way back, and after that a lot of modifications have happened on the data in that column. Now you might need to resample and rebuild your statistics. The default SQL Server will rebuild statistics whenever the number of modifications on a column reaches 20% plus 500. Now the 20% here is 20% of the values in that table when it last built statistics. So when for example, let's say you had 1,000,000 records in the table when you built statistics, 20% of 1,000,000 plus 500. Whenever the number of modifications, when I say modifications here, I mean an insert or an update or a delete occur on this column, which exceeds this value, and a query comes to the server where this particular threshold has already been surpassed. When a query comes to the optimizer, before he builds the plan, he will first rebuild the statistics and then build the plan. A word of advice here, instead of using the auto build statistics, I know this is a recommendation from Microsoft as well, that is good to have the auto update and auto create statistics set, but I would say if you can have the ability to understand which columns are used frequently in where conditions, which columns are frequently used in join conditions, and do not have indexes, and if you can manually create statistics for these columns and also manually schedule programs sorry, manually schedule programs to do the updates, you will get a bit of control where these are happening at the time when you want them to happen. Because the problem with the system automatically building statistics or rebuilding statistics is that this could take place during peak hours. It could take place during the peak operational hours, slowing down user queries and using resources on your server at times where you don't want these resources to be used. But by you scheduling them, you would have the ability to schedule them at non-peak hours or intervals where you know there is low activity, and thereby keeping them updated. However, if you want this to work successfully, you will need to ensure that you are well aware of when statistics will get outdated, and rebuild them before such thresholds are met, so that your execution plans that you create don't turn up to be wrong. So that's a bit of information about statistics and how you actually work with them. Now what is left is for us to understand a bit of execution plans. We'll do that in a couple of seconds from now, where we'll create a couple of complex queries and see how to work with execution plans. Okay, I'm into my virtual machine and I've got a couple of scripts opened up here. We're going to use the scripts to try and understand execution plans and how to read them. What I'll do is I'm going to start off by using my sample database called credit, and I'm going to execute a stored procedure which is going to clean up this table in terms of statistics and indexes. So I've deleted and dropped all statistics if any were there, and also dropped all indexes if any were there. I'm now creating 3 non-clustered indexes on this table called member, on the first name column, the corp number column, and the member number column. So 3 non-clustered indexes now on the first name, the corp number, and the member number. I'm waiting for that to complete. Excellent. I'm going to turn on the statistics here so that we can view the output of statistics for the IO at least. And I'm going to execute one query here which is trying to pick up where the first names start with Q, the corp number is greater than 450, and the member number is greater than 8,000. Now I want you to remember that we have indexes on all these 3 columns, the first name, the corp number, as well as the member number. So keep that in mind. I'm going to go to the query here and I'm going to include the actual execution plan. And let me just execute this query now. And we get just one row from this query throwing up. And I go to the execution plan here, and the execution plans are always read from right to left and from top to down. So let me just expand that so that I explain to you how this query worked. Now, in terms of looking at this, it's very clear. We had three indexes, one index on corp number, one index on first name, and one index also on the member number. So we had three indexes that we created, and we also had three where conditions if you're looking at the query. Just to open up that query there so you can see that query in clear. So we've got the query there where three where conditions on three columns that have indexes. Now the system or the execution plan that was used ultimately to execute this query, it used the corp number index. So it used this particular index, which is the corp number index. You can see that out there. It used the corp number index. It used the first name index. You can see that here. So you can see two indexes got used. However, it never used the member number index. Now, in terms of selectivity, if you look at the corp number index, the total rows in this table are 10,000. Now, in the 10,000 rows, the estimation here said that this index where the where condition corp number is greater than 450 will throw up 303 rows. So he used the non-clustered index and he picked up those 303 pointers from the leaf level of the non-clustered index. He used the first name index. Again, you notice here the estimated number of rows according to this was 26. Was 411.765. That's the estimated number of rows. The actual number of rows that threw up was 411, so that's a pretty close estimation actually. So he used this index. So here he got 303 pointers. Here he got 411 pointers. Now at this stage, guys, it's important to understand he didn't assess data pages. He only used the non-clustered index. So most probably the max to max, maybe one root page, one leaf page. So two pages were assessed in the corp number index and maybe two pages, or since it's 411 rows here, that depends on how many rows fit on a page, how many pointers fit on a page, maybe three. So all in all, the max number of pages he's used here were around 5, 4 to 5, okay, for both these indexes, using the corp number as well as the first name index. He's only touched the root and leaf pages related to 303 rows and 411 rows. And since this is a query which is talking about greater than and the values are in a range, they would all be together. So it's safe to say that it would have picked up all the 303 rows from one single leaf page, and maybe all the 411 too from one single leaf page, or maybe two at the max. That's why I said 4 or 5. So one root, one leaf, one root, and maybe one leaf, or max to max 2 leaves. 5 pages were touched. But what does he have at this point of time? He has a set of corp numbers and the addresses of where you can go to get the record. He has a set of first names which start with Q and the address where you can go to fetch it. Now our condition is an AND condition. The first name has to start with Q and the corp number has to be greater than 450. What he does next is he does a hash match inner join. You can see that operation here. Now the hash match inner join operation does a join on the pointer, not on the key, because the addresses are common. So very logically speaking, if I have the same address for first name which starts with Q and that same address is also for where a corp number is greater than 450, it means both the conditions match. So the hash match inner join here is he tries to basically match the addresses and find addresses that match both these outputs that were there in both these outputs. When he does this, he picks up 12 matches. So he's got 12 addresses with him where the first name is greater than, is like Q, starts with Q, and the corp number is greater than 450. So total values where both condition matches, he's got 12 addresses. Still no data pages have been accessed. Now he does a nested loop here where for each address he does a row ID lookup on the heap, because we don't have a cluster index here. So he does a row ID lookup on the heap and picks up each address which is here. While he's picking up each address, he will check to see whether the member number is greater than 8,000. And after that, the actual number of rows that he returned was only equal to 1, which you can see right now here. So out of the 12 rows which he read from the actual data pages, only 1 row matched the condition where member number was greater than 8,000. So he's hit 12 data pages. He's hit around 5 index pages. Okay, 4 to 5 index pages. So you're looking at a total IO of around 17 pages. So the nested loop here was to loop and read each page from the data. Let's have a look at the IO here. And you can see the logical reads here were equal to 21. Now that's the IO which was used for this query. 12 of them were data page reads. The non-clustered index here could have been 2 pages or 3 pages depending on whether they were intermediate pages involved. Okay, and here you had again 2 pages, 3 pages or 4 pages depending on whether there were intermediate pages involved. So if you assume that there were 3 pages for corp number, that is 1 root, 1 intermediate, 1 leaf, 4 pages for first name, 1 root, 1 intermediate and 2 leaves. You've got 7 pages right here which was used, and you've got 12 pages for which it assessed for the data. There is your IO of 21. You can see how clean and simple it is to actually understand an execution plan. So hope that seems easy and you'll be able to read execution plans from now. I'm switching back to my PowerPoint slide. So we did stats already and execution plans. We've understood what execution plans are and why they are used. Now these are some of the options which you need to understand. A table scan icon tells you that it actually went to the IEM and read all the pages that belong to the table. That's what it means when you see table scan. A clustered index scan is very similar to a table scan where it reads all the data pages. The only difference is these data pages are the pages which are in the leaf level of the clustered index. So when you see a clustered index scan, don't get too excited about it. It's on par almost with a table scan, with the exception that these were organized pages. So it read all the pages that belong to the table, but this time it read it in the leaf level of the clustered index. Yeah, you need to be happy when you see clustered index seek, because when you see this, it means it went to the root page, searched for the pages where the records were available, and then basically read from there. So a clustered index seek is good. It means it went to the root, searched for your records, searched for the specific pages, and then picked it up. We also have a nested loop inner join, which I just told you about. A nested loop inner join is majorly used when you have one small output and one large output. So it picks up one value from the inner table and loops it with the outer table and searches for it in the outer, searches for a match in the outer table, and it loops this until all values in the outer table are exhausted. So sorry, let me just give you clarity on that. It picks up a value from the outer table, scans it in the inner table for a match, and it loops this consecutively until all values in the outer table are exhausted. RID lookup is when you're trying to find data on a heap. You've got the address, you know which row, you know which page, you need to go and read that row from that page. We call that and refer that to a RID lookup. This happens only on the heap. A key lookup is when your data is not stored on a heap and is stored in a clustered index, and your where condition is using a non-clustered index, which throws up the clustering key. Now it needs to pick up that clustering key, go to the clustered index and search for that particular page to pick up that record. So you will see a key lookup clustered in such cases as the icon on your execution plan. Join operations, apart from loop, you have the merge join operation, which is good when you have two sorted result sets. You have the hash match when you have two unsorted result sets. The hash match join is good because it creates hash buckets and the matching is much faster. This is good when you have two unsorted result sets. We also have a stream aggregate. This is a highly efficient method in which is used by the system in order to basically aggregate your data as they come into the system. It's called the stream aggregate. And we also have the hash match aggregate, which is a hash table is created to aggregate the data, and it's not done through streaming the data as it comes in. The hash match aggregate is lesser efficient compared to the stream, but for the stream aggregate to work, you need to have the data already in the correct order so that it streams through and you continue to basically process it. It's faster naturally, but the cost here is the data needs to be already sorted in on the group by column. Before it comes in to the stream aggregate. The hash match has no such requirements. It's costlier, but would be able to do this for you without the data being sorted. We also have a filter, which is a typical filter used for any where clause predicates or having clause predicates that you can pass. We have a sort operation, which allows you to sort the data and order the data in your system. And in case you're doing modifications, you can see an insert icon or update icon or a delete icon like what you can see right now. There is also a select icon which you would be able to see when you're selecting data. So that's the data modification which you can actually work with. And one last thing now is before we wind up this session is partitioned indexes. Now, assuming you're already comfortable with partition tables, the whole concept here is if I had a huge set of values, and most of the time, let's say I was operating in multiple countries, and I've got the city names of all these countries where people make where conditions on. And unfortunately, this table has maybe 1 billion records for each country. And let's say you're operating in 100 countries, so you are looking at 100 billion records. So when someone makes a where condition on the city column now, it needs to go to an index which has 100 billion records for the entire 100 countries you're operating in, and try to find the key matches. Now, in such scenarios, it would be great if you can partition that index, where you partition the indexes by using a particular range. In this case, it would be for each country. So what would happen is, when you make the where condition, depending on which city you are asking for, it would use the appropriate partition in order to basically pick out that data. A more popular example could be time, where you partition by each year, so that your indexes are smaller. So every partition will have its own root page, its intermediate pages, and its leaf pages, thereby ensuring the number of index pages you need to assess to retrieve your data would be far lesser compared to you trying to build all of this into a single partitioned index. It is highly recommended that for ease of use and ease of maintenance, that you create index aligned partitions, where your indexes are completely aligned with your tables. Now, what we mean when we say this is, you create the table partitions and you create the index on top of this using the same ranges as your table partitions. This means your indexes and your tables both have the same kind of partitioning. This is called an indexed aligned partition, and this would be easier to maintain and easier to work with. However, you don't have to do this. You can also basically have indexes partitioned completely differently compared to how the data is partitioned. Now, that's about partitions and partition indexes, and with that we've actually come to an end of this session. Let me thank you all for attending this session and spending your valuable time here. Hope to see you in all the other video sessions that we have during the series. Thank you again. You will be ending with one last quiz. So thank you so much for attending this session, and bye bye.